Today we're going to talk about fixed volume open box with square based example. Let's say a box with a square base and open top must have a volume of 4,000 cubic centimeter. Find the dimension of the box that minimizes the amount of material used. We hear the term minimize, which is an objective in optimization. As far as application goes, let's say a certain product is being packed into boxes in a factory. Minimizing the amount of cardboard, which is the surface area of the box, reduces the cost. We are going to compute the surface area for each x value using this formula, when x is the dimension of the base of the box. 4 times x times h, where x is the dimension of the base and h is the height, gives me area of the 4 balls. Add that to x squared, which is the area of the base, and that gives you all the surface area of the open box. Now, the height of the walls is restricted by the size of the base given by the constraint h equal to 4,000, which is the volume, divided by x squared. Why? Because volume is equal to 4,000, and that's equal to x squared times h. Therefore, the formula for surface area in terms of x only is, instead of 4 times xh, we're going to have 4 times x times 4,000 divided by x squared plus x squared. After simplifying this formula, x in the numerator and x in the denominator in the first term simplifies, and you end up with 4 times 4,000 divided by x plus x squared, or 16,000 divided by x plus x squared. So let's try to give a few examples. Let's say x is equal to 30 centimeter, then the surface area is going to be the surface area of the 4 walls, which we found it through that formula, is 16,000 divided by x, and then added to the area of the base, which is x to power 2. For x, we plug in 30, and we get approximately 1,433 centimeters squared. When we make x a little bigger, the height is going to be a little smaller. So for x equal to 40, you can see the walls are going to be smaller because the constraint relates x and h. The surface area is going to be computed as 2,000 squared centimeter. This is a little bit more expensive than the one before. So we saw that for bigger x, as x goes bigger, the surface area increases. Now let's go back and decrease x a little bit. For x equal to 20, if I plug it into the surface area formula, I get 1,200 squared centimeter. So price decreased. But I don't know if this price decrease is going to continue. So I'm going to just try another one. For x equal to 10, look at the walls. They're very tall. When I plug in, it's more expensive than it was, or the surface area is more than when it was x equal to 20. I can try in x equal to 15 and then see that the price decreased a little bit from x equal to 10. But with plugging in different numbers, I cannot ever be sure. At this point, if you are a pre-calculus student and you want to find this minimum surface area, the only thing that you can do is to graph the function. Again, remember, constraint is 4,000 is equal to x squared h, which means h is equal to 4,000 divided by x squared. Objective is s equal to x squared plus 4xh. If you're a pre-calculus student, you need these two on your paper. Then you need to compute the surface area function, which is by plugging in h into the objective, which is going to give you x squared plus 16,000 divided by x. Need to figure out what the domain is in this case. Obviously, x equal to 0 is not included, but also x cannot be negative. So domain is all the positive numbers. Graph this function. I plotted the function in Wolfram Alpha, and here's the result. By the way, Wolfram Alpha is very easy to plot. You just say plot and the function. Notice that for x bigger than 0, I cannot find a minimum easily in here. I can kind of see, look at this, with a horizontal line, I can see that actually a bunch of things are under that horizontal line. And horizontal line is crossing the graph. In Wolfram Alpha, I cannot enlarge the graph neither. But I have something better. I can actually look at the minimum of the function in Wolfram Alpha. And it graphs it again, and it gives you at x equal to 20, you arrived at a minimum value right there. So far we have the constraint objective function, and we looked at the plot, and we computed the minimum on the graph. So minimum of the objective function is achieved at x equal to 20. That makes the dimension of the box with minimum material 20 times 20. Plug in 20 into the h function right here, and h becomes 10. This is good enough for a pre-calculus course, but it's not good enough for a calculus course. What comes next is the entire work that you need to put on your Calculus 1 homework or exam. So let's find the solution Calculus 1 way. You start with the same song and dance. You find the constraint. You use the constraint to find h. You find the objective. You use the constraint to actually make the objective function of one variable. Then you take the derivative of the objective function. In this case, derivative of x squared is 2x. Derivative of 16,000 over x is negative 16,000 over x squared. And the next part is to find the critical value, which is by setting the S prime equal to 0. Before doing that, make sure to combine the two terms and find the common denominator, which we did this here. Then set the numerator equal to 0 to find the 0 of S prime. Setting the numerator equal to 0 gives us x is equal to 20, which is a value within the domain and is a critical value of the function. Use the constraint, plug in the 20 into the constraint to arrive at h is equal to 10. Perform the first derivative test to ensure that the minimum of s is achieved at the critical point x equal to 20. Without this, you don't know if you have a minimum, maximum, or neither. So draw a number line, exclude x equal to 0 because it's not part of the domain, shade the domain to the right of x equal to 0, mark the critical number x equal to 20 on the line, get a test point, let's say x equal to 10 to the left of the critical point, which you arrive at s prime of 10 is less than 0 by plugging in 10 into the derivative. Then plug in a value to the right of the critical point, which 30 is a good number. S prime at 30, if I plug into it, S prime 30 is bigger than 0. Therefore, you see in the domain before the critical point, the function is decreasing. After the critical point, the function is increasing. Therefore, critical point is a minimum point, or is the value that makes the function minimum. X equal to 20. Dimension of the box is going to be 20 times 20 times 10.